Right? Remember tomorrow your tests are AC and electromagnetic induction. After that, we will do person waiting there. Hi, David. Hi, on your way. Good effort.
David is in the house.
David in the house. All of you are still in the house. Only we are.
Drago.
Hi, on your way. Good effort. Okay, let's carry on. Right? Essentially, for this topic, you have to remember what is a photon. Right? There's a symbol for photon. And just memorize it. Photon, packet. Right? Just think of it like water, a packet of water, you know. Photon in a small world of atom molecules. We have to work with photon. That means the wave becomes smaller like that. Weakly there. It's a packet of energy of electromagnetic radiation. That's what photon is all about. And the energy is given by H times F. H is called Planck's constant. That's the value, 6.63 times 10 to the power minus 34 joule second. And then F is the frequency of photon. So don't be surprised even in exam, the AS exam, they tell you all this and then they ask you to find the unit for Planck's constant. Right? Matter of time only. Coulomb's law has come out and they are asked to find the unit for the constant. So matter of time only. Okay, so then you should be able to calculate using this formula. Basically, all this formula only. C is F lambda for the wave. And then you need now to calculate the energy. E equals to H F. Right? And then replace F with C over lambda. Then put in the value for H, value for C, and then 700 nanometer, change it to SI unit, and calculate out. Right? Usually coming out, they will ask you to calculate that. Okay. Then we come to wave and particle. How do we know? It behaves as wave, where we can have interference between two waves, or diffraction, where the wave passes through a slit about the same size as the wavelength. That's diffraction. Then we will study photoelectric effect and X-ray, and even energy level. We have to think of electromagnetic radiation behaving as particle or particulate nature. Packet of energy. And then we start with photoelectric effect. We say it's the emission of electron from a metal surface when illuminated by electromagnetic radiation of certain energy. Right? Certain energy, not all energy. Right? There's your electromagnetic radiation coming in, and there's your electron emitted. Okay, and then we just went over with you roughly why you have a certain amount of energy required to release it. Right? And we call that energy the work function. We say that, okay, in the metal, these are your positive ions. Right? They are fixed in position, they vibrate. And these are the free electrons. Right? They are what I call delocalized. They are not tightly bound, they can move around. But as they try to escape, there is going to be attractive force by all these surrounding neighboring ions that there is no chance they can escape. Right? But if they have been given energy by heating it or electromagnetic radiation, give it energy, then it can escape. Okay, last it to you. We call that the work function minimum. This one you have to memorize. minimum energy of photon or minimum energy of electromagnetic radiation to cause emission of electron from the surface of metal with zero kinetic energy. That's important. Right? Energy of photon that cause it to be emitted with zero kinetic energy. And that is your Planck's constant. That's what I call threshold frequency, F0, minimum frequency. Okay, so this is the term that you need to remember. Minimum frequency of electromagnetic radiation for electron to be emitted from the surface of metal. Okay, we want to show you that electron in different part of the metal, yeah, they will receive the electromagnetic radiation. But remember, as they move up to the surface, they will lose energy. That's why they are not emitted with maximum kinetic energy as they exit the surface. Right? Energy is now a bit lower. That explains why we have a kinetic energy of electron from 0 to a maximum value. And then different metal have different work function. Cesium is 1.9, beryllium is 3.9. And then we went to give you some idea how to think of it. We can think of potential well and work function. You can think of it like this ball there, or this electron there has to jump up to that top there. And the side are all very smooth. Yeah, it cannot jump midway and then jump again. Right? So this is the minimum potential energy, or we call it work function, that this electron require, or the person required to jump to the top there. Right? So that's the work function, and that is the energy. Right? This is the energy given by this electromagnetic radiation. And when the electron escape, if that is the energy of the photon, the electromagnetic radiation energy, then this is the amount given to the metal work function, and that is the maximum kinetic energy of the electron. Okay, and then we summarize that with Einstein's photoelectric equation. Is the maximum kinetic energy of the electron that is emitted. That's the energy of the photon, and that's the work function. Just think of it like you are braking a car. If your speed is larger, then you can exceed a certain distance. So that is the purpose of this work function there. So you have to give it the amount of energy to the electron before it can escape with that kinetic energy. Right? So basically this is a formula for conservation of energy. Okay, so now we look at the equation. Right? The equation, Einstein's photoelectric equation. We basically you change the frequency and then you just measure the maximum kinetic energy of the electron emitted. That's all. H and phi, our work function, are constant. And we compare the equation of straight line. So that's your y, x is your f, h is your gradient, and then work function is your c. Okay, and then where this part is where your y is 0. Right? So if that is 0, then this is your h f naught, no? H f naught, no? So this is your f naught, no? Okay. Then usually they will ask you either a lower work function or higher work function. Where is the graph? Right? Remember, the gradient doesn't change. The work function can change. So that's why we get still a straight line, but greater work function further down, that's all. Okay, you can go to this one if you want to see the simulation, how they draw for you all the experiment.
Yeah, there's one allocated for me. I request. Some people is classroom, right? Yours is where? Classroom. Ah.
Okay, and then we calculate this one. Right? For function of barium given, you should be able to calculate. This one you need to memorize. Remember electron, that's all. Charge on electron, change to joule, that's all. And then 3.9, you just times 1.6, convert to joule. And then threshold frequency and threshold wavelength, just using the formula, that's all. That's your work function. Put your value inside there. Okay? Value for energy, W. That's your Planck constant. You can find from your formula sheet. Then your F naught, calculate out. Then after that, use your wave equation. Speed of light is frequency times wavelength to calculate your wavelength. Okay, so far, stop me if you need to ask question. Okay, if not, let's carry on. Right, review electromagnetic waves. That is the rate of energy emitted. That is the, or if you like, that's the energy falling, rate of energy falling on that surface there. Right? That's the surface area of the surface, perpendicular. Then we replace this power, right? Rate of energy, E divided by T. That is your surface area. Right? Remember the intensity, light is energy. The wave is falling normally on the surface. So we can see that increasing the intensity, increasing the intensity increases the energy given to the electron. That's the energy given to the electron. That's our definition for intensity, energy per unit time falling normally per unit surface area. And we know that intensity for wave is proportional to amplitude square. So greater amplitude, morning Reggie. Thank you for being able to come. Right? So intensity is proportional to amplitude square, greater amplitude, greater intensity. Right? That is our K is our constant. That is your surface area. Okay, so in quantum theory, to explain photoelectric effect, we just think of the electromagnetic radiation, right? Just like a packet of water where you throw at your friend running around. Right? So we can think of it as electromagnetic radiation as photon of fixed energy. So it can be one packet, two packet, three packet, and that energy depend on the frequency. Right? Energy of the photon depend on the frequency. E equals to hf. And the energy must be completely given. Just like I throw the packet of water on you, you all get wet. The packet of water disappear. No more already. Only the plastic bag left. So same idea. When the photon meet the electron, if there is enough energy, it's given to the electron. And then the photon disappear. Then the electron escape. Right? But remember, both are small. Photon and electron are small. So some photon may not meet electron. So they just pass through. Right? That's our symbol. We think of it as small, tiny wave. That's all we like. Packet of energy. Okay, so now the intensity depends on energy of photon. Right? We have to modify our equation now. Number of photon, MP, falling on the metal surface, not only on energy, but number of photon. Right? We haven't changed that. Energy is still the same. energy per second falling normally per unit area. Same. Intensity P over surface area. But we just modify the all to include NP, number of photon per second, energy of photon E. Okay, so P is total energy, this number of photon, this is the energy of each photon, that's still the time. Total energy divided by time. Okay, so now we can see if I increase intensity, right? Keeping the frequency constant. That means if I keep the frequency constant, I'm keeping E constant here. Okay, right? We keep the intensity constant, and we use photon of particle energy or frequency constant, right? Sorry, if we increase the intensity, increase this one, sorry, increase this one, keep the frequency constant, that means we keep this energy constant, right? If we increase that, and we keep this one constant, that means this one must increase, so increasing the number of photon per second. Okay, let's illustrate it here. There's your beam of radiation falling on a metal surface. That's the equation. Right? Now we just rewrite it, the full equation. Number of photon, energy of photon, divided by your time. Right? That's your total energy divided by your time. That's your surface area. That surface area that the light falling on or the energy falling on. Okay. So if we keep frequency constant, we increase that one. How can we change that? Because our area is still the same. So it means that this one must increase. Okay. Number of photon falling on the surface must increase. Okay, then let's see if it's wave, different. Wave, this is the total energy. Right? If we increase the intensity, we are increasing the total energy falling on the surface. Likewise, if the number of photon falling on the surface is constant, right? MP over T, but the energy of photon is increased by increasing the frequency, the intensity on the surface is increased. Okay, we can look at the same formula again. Right? Number of photon on the surface is constant. NP divided by T is constant. Energy of photon is increased, E increase is one, right? By increasing the frequency, then we are increasing the intensity. Okay? You with that so far? Okay, you're happy, let's carry on. Right, we can do experiment. That is your zinc plate. Usually we will use ultraviolet radiation, and that's your this. Right? Initially, we will charge the gold leaf negative. Right? Electroscope. We usually have to clean the plate first, and then place on the electroscope, negatively charge the zinc plate. Then we shine ultraviolet light on the zinc plate. And then we will observe this gold leaf will go down. Right? So why does it go down? The reason why is diverge. Right? Why is why apart is because this is negatively charged, this is negatively charged. If the gold leaf goes down, it means that this electron must have been ejected from the surface. So as the number of electrons is emitted, then the repulsive force between these two metals is going to be less. So the divergence will decrease. Right? If we charge it positive, nothing happens. Anyone like to try to explain for me why nothing happened? Yep. Anyone? We charge the zinc plate positive and we shine ultraviolet light on it. Nothing happened. Anyone?
Because there is no electron.
The electron or what?
There is no electron because it's positively charged. The electron already emitted already.
No. Thank you, Janjun, for attempting to answer. We have electron. Right? The ultraviolet light also will emit the electron. But what's the problem? As the electron ejected, remember this is positively charged. So who is stronger? The positive charge will attract the electron back. Right? Positive plate will attract the electron back, so electron cannot escape. As it escape, it pull back. So how to escape? Okay. So we
So I
can.
don't understand. I don't
Say again.
understand the previous one.
Which one? The
The
previous one.
UV light one.
You mean this one?
Yeah.
This one is just observation only. What we do is we shine visible light, nothing happen. We shine ultraviolet light, we see this gold leaf start going down. Right? Remember the gold leaf is initially charged negative. You charge negative, the charge will appear on the leaf, and because both are negative, they repel each other. So when we shine ultraviolet light, we see the gold leaf goes down. So how to explain it? The electron must have been ejected. So as more and more electrons get ejected, the repulsive force between these two metals or these two leaves become less and less. So the divergence will go down until no more electron, then it will go back to its original position. And
So why go down? Because
electron
the
emitted.
zinc plate is negative.
Electron is emitted.
Emitted to where?
Initially, it is negatively charged, so they repel each other. But remember, if you shine ultraviolet, electron is emitted. So as more and more electron
Oh,
emitted, the repulsive force become less. So it slowly will go down.
the electron from gold leaf will go up.
It will be ejected from the disk. So more electron will go to the surface there, and then it got ejected. Okay now. Okay,
Okay,
let's
sir.
carry on. Right? Various way of showing the two experiment. Right? As I say, you can show it this way, it doesn't matter as long as there's a gold leaf there. Okay, 10 minutes time we have to change to another zoom. Right? So we can use laser, we can use visible light, we can use ultraviolet light. Right? Only with ultraviolet light on the zinc plate, these two no effect, visible light and laser no effect. Right? Only this one got effect. So it means that electron must have been ejected by the ultraviolet light. Okay, so that's our explanation. Electron emitted are, if it's positively charged, the electron emitted will be attracted back. So the gold leaf doesn't go down. But if it's negatively charged, the electron is emitted. If the gold leaf, the electroscope, lose electron, so the repulsive force between the leaves become less, right? And the electron will be electron is not going to be attracted back if the electroscope is negatively charged. As it's emitted, it's repulsed, so it won't come back. Okay. So in this one, you need to know your electromagnetic spectrum. Sometimes they may ask you to identify the radiation. Right? This gamma, X-ray, ultraviolet, there's a visible, there's a infrared, there's a microwave, and there's a radio wave. Communication, we concentrate on these two regions. Okay, remember, when we say minimum frequency, it means maximum wavelength. Remember our C equals to F times lambda. Okay. Minimum frequency, that must be larger, inversely proportional. Okay, then on you might need to remember for your AS. Then we can investigate effect of different electromagnetic radiation on different metal. Different value of electromagnetic radiation or different frequency on different metal. You can use zinc, can use sodium, can use cesium, and we can shine electromagnetic waves on them. And then we can tabulate it out. X-ray, yes, for all these. Ultraviolet, yes. Cesium, no. Ultraviolet cannot do that. Whereas for visible, higher frequency, yes, for sodium. Orange and red, longer wavelength, no. Okay, whereas you can see, for others, visible, infrared, radio doesn't cause emission for cesium or zinc. Okay, this experiment just show you there's a minimum frequency involved here. Okay, minimum frequency. Longer wavelength there. Okay, which is a longer wavelength, red or blue light?
Red light.
Yeah, good. Okay, so our conclusion for a photoelectric emission to occur, the radiation must be greater than a certain minimum wave frequency or less than a certain maximum wavelength. Okay, minimum frequency or greater than a certain maximum wavelength. So usually it's ultraviolet, X-ray and gamma that will cause the photoelectricity, not visible. Okay, laws of photoelectric emission. These are experimental observations. Right? What are the parameters or what are the variables? Right? We have number of photons falling on the metal surface. That's the intensity, number of photons with the particle energy, and then the frequency of the photon falling there. Then we have electron emitted per second, and then we have the energy or maximum velocity of the electron emitted. Okay, first thing is emission is instantaneous. Doesn't wait. As soon as you shine the radiation on the surface, it's emitted already. That's what we observe. And then we know that there's a threshold frequency below which no emission. That's my short form. Right? For emission to occur, the frequency of electromagnetic radiation must be equal or greater than the threshold frequency. And maximum electron kinetic energy depend on frequency. And remember, all these are observations. We must have a theory to explain them. Maximum kinetic energy does not depend on intensity. That means I can increase the intensity of light. If there is no emission, there is no emission. I cannot force a metal to emit electron. Right? So that's why maximum velocity of electron is dependent on frequency, independent of intensity. That's my short form of writing it. Rate of emission of electron depends on intensity. Right? So that's short form. Number of electron emitted per second depend on intensity. Okay, so we must have a theory to explain all of them, not some of them. then there's a good theory. Okay, how to explain instantaneous emission? There's no time lag lah. Not like you have to wait, traffic light go green, and then you are waiting in the car there. You have to wait for a while before for the front car to move before you can go. There's kind of time lag. Okay, thanks for reminding me, Ganchun. We will finish one or two and then we will stop. We still got about 2 minutes. Okay, how do we explain? Wave model, as the wave meets an electron, it gives energy. As sufficient energy is received, the electron emitted. Right? Remember, our wave model is just like heating water. You cannot have the water boil very fast. It has to take time. So in this case, the wave come in, give the electron energy. They are very small, the wave and the electron that they need, they give more and more energy. Then when sufficient energy, escape. So wave model will predict a time lag there. It will not emitted instantly. So false, right? Contrary to fact. Whereas wave model, each photon has a fixed energy. So if the energy is enough, it will be given to the electron. And then the electron emitter, as long as enough energy, it just escape. Instantaneous. Okay, I think I will stop here. Give you 5 minutes break. Then we will carry on. Anything to ask? If not, I will stop here. Carry on in 5 minutes time. You want to go for a break? Go ahead. Okay, I'll stop now. Got question to ask? You can ask.